Welcome to the Open University campus, and in particular, welcome to our S111 live debate. Hello also to our online audience. My name is Maria Velasco. I'm chairing the first presentation of S111 Questions in Science, working with a fantastic team, many of which are here today. We hope that you are enjoying the module. You have just been studying the topic, is there life on Mars? And here we are going to take the question a little bit further, just reaching out into a space to ask, which is the best place to look for life, icy moons or Mars? Our Master of Ceremonies for the rest of the afternoon is Dr. Janet Sumner. Janet is a geologist and a volcanologist, and she works with the Open University as a media fellow. So without any further ado, over to you, Janet.
Thank you, Maria. Welcome to those in the room and all of you joining us online and through social media. To get us underway, we're going to take an entrance poll as everybody takes their seats. And you join us online. So, studio audience, you should have two voting cards, a red planet for Mars and a blue one for icy moons. Online watchers, you should have something similar on your voting widget, and you can start voting right now. And this is the big question we're debating today. Do you think Mars is the best place to look for life? If so, raise your red planet cards. Monica's already raised hers. And vote online. However, if you think Mars is a dead duck and your hopes or fears for life in the universe rest with icy moons, please raise your blue moon cards. Ooh, or click online. So, those of you in the room are voting now. Keep those cards high and clear so we can do a rough count. Now, if you're feeling particularly passionate, and I think some of you possibly are, one way or the other, feel free to wave your cards around while we do a count. For all of you voting online, use your voting widget on your screens and vote now. It's going to take us a few minutes to collate the studio votes and your online votes. So in the meantime, I'm going to introduce our two PhD students, Alex and Peter, who will be manning the social media desk throughout. They'll be fielding your questions, keeping an eye on the chat rooms, and checking the Twitter feed, the hashtag for which is S111 Live Debate. Okay, well, in the room here, it's looking like a very clear win for icy moons. Oh, there's one or two determined people hanging out for Mars. Alex, Peter, what are people saying online?
It's pretty close to what we've got in the room, actually. At the moment, it's about 70% for icy moons, 30% for Mars.
And it's the same on Twitter.
Okay, so icy moons it is then. Let's see if the debate can change your mind over the next couple of hours or so. So just a word to all of you joining us online. You're very much part of this debate. We want all your contributions. So please join the argument, access our social media, give us your questions, thoughts and opinions that we can put to the academics on stage. We want you to feel like you're here in the room with us. If you're radically opposed to one idea or tremendously supportive of the opposition, let us know and we'll make your voices heard. Right, now it's time for me to introduce our four speakers, who are Open University scientists with a keen interest and an international reputation in this field of study. So, ladies and gentlemen, please give a warm reception to Professor Monica Grady, Dr. Suzanne Schwenzer, Dr. Karen Olsen-Francis, and Professor David Rothery. Now, These academics are each going to present a case in turn and will be available to answer questions. Those of you online can start sending your questions now. Those of you in the room, it's fingers on buzzers, but please hold your questions until we get to the live Q&A session, which will come after you've heard each of the 4 speakers deliver their piece. Now, to add a bit of spice to life, we're going to ask the audience here in the room to decide which of the teams will present their case first. So in the room, if you want Mars to go first, red card nice and high. If you want icy moons to go first. Oh, and it's looking like Mars will be going first. So I'm going to ask Suzanne to kick off the whole debate. Over to you. You have 7 minutes to impress us, and I'll be giving you a 2-minute warning.
Thank you. That's a hill to climb for me. And I want to start with asking the question, why are we looking for life? We are looking for life because we know this picture. This is a picture that the Apollo 8 astronauts took. And what you are looking at here is the Earth as a little blue fragile marble in front of the vastness of deep space. And the big question is, are we alone? Are we really the only ones alive with all the life around us that we know or not? On the next slide, you see a planet that is actually quite similar to Earth. It's Mars, yes, and it has polar caps just like the Earth. So we know there is water there. And the polar caps change with the seasons. So Mars has water and seasons, just like the Earth. And it has an atmosphere. You see a little bit on that slide, but you see even more on the next picture, where you see a map of Mars, and you see dust clouds over here, and you see water ice clouds over here. So we've got an atmosphere. It's much thinner today than it was in the history of Mars in the very early beginning. And I will show you and try to make a case. There was water, there was conditions on Mars that were conducive to life. And there is Gale crater indicated where the Curiosity rover sits, and a lot of evidence comes from that. Next slide. But there's even more. There are volcanoes on Mars. Volcanoes on Earth are places where there is hot water, where there is fresh rock coming to the surface, providing nutrients, providing places where, for example, microbes can live and kick off a food chain right there. Next slide shows an impact crater. This is Gale crater on Mars, a large 150-kilometer diameter impact crater. And yes, they are very violent when they happen, but shortly thereafter, you've got hot water in the underground, you've got maybe a hole that forms a lake. And on the next slide, you see Pillinger Point. Yes, Pillinger, Colin Pillinger, was here at the OU looking at Mars, looking at the organics and whether Mars could have been habitable to life. And so this place was named after him. It's the Rim of Endeavour crater, and we found places here where there is hot water coming to the surface as the aftermath of the impact. And where there is hot water, there you have all the nutrients such as carbon, nitrogen, but mostly also calcium, sodium, everything you know that we need. And it's all those places that we can look at, and we really know where they are on Mars because we are studying Mars for the past 40 years. So on the next slide, you see what we know about Mars. We know about the Martian atmosphere. We've measured the Martian atmosphere and calculating back from where the Martian atmosphere is today, very thin, but it's there, to what it has been 3 or 4 billion years ago. And we come to the conclusion that there was lots of water. Exactly how much is under debate, but that's probably the maximum amount that was there. So we had maybe a huge ocean, maybe it were isolated large lakes, but standing water on the surface. Next slide, please. And we can find evidence for that. We see from the orbit, and here you see a 2-mile scale bar. We see meandering rivers, just as we know on Earth. Rivers that flow down the hill. Well, this could be intermittent flash floods going down there, which wouldn't be that good for life. But we at least know there is flowing water, and it's in many places. You can go and look at a map of Mars, and you will find them over and over again. So on the next slide, you see that we can look even closer. That's now again in Gale Crater, and all the hardware that you see here is pieces of the Curiosity rover. This is a 360-degree panorama, so you see wheels all over. But what you really see is the geology. You see all these layers, and these are sediments from a lake bed, interspersed with sediments that were laid down by wind. So we know there have been changing conditions, but we know there are mudstones which store water and which have been laid down by a lake. Next slide. But it gets even better, because if you look at this picture, this is actually my absolute favorite. You see that there are little round pebbles. This is now 5 centimeters. So this is a little round pebble that size. And little round pebbles on Earth always form when you have sustained water flow at the surface. They form at beaches where the water goes back and forth, and they form in rivers where the water flows down. And if the water flows down a river for a sustained period of time, then you know you have long-standing conditions where life could evolve even to higher life. But what about all this red stuff? Red is oxidizing, it's harsh, it's something that wouldn't actually be conducive to life. But we've drilled on Mars. This little drill hole is only 2 centimeters deep, and what comes out there is gray. And gray is reducing, is much better for life. It's not as harsh, it's not as irradiated. So we know that what we see of Mars today is the skin of a really harsh oxidizing environment. But just under this skin, we could have conditions that geology provides us that are clays with water in its structure, formed by water, laid down by water, and actually in reducing benign conditions that we know life on Earth exists. Next slide. And we know even about more water. These veins, white things, calcium sulfate veins that are showing us what type of water was flowing there. And I'll end handing over to Monica, who will take over next with the next slide, showing you we have spacecraft around Mars which study all of this from the surface, the Curiosity rover, and that's Trace Gas Orbiter looking at methane on Mars. Thank you.
Suzanne, thank you. We're actually going to do the case for and against, so I'd like to ask Dave now to step up and present the case for the opposition.
Thank you, Janet. Well, I don't think Mars is a bad place to look for life, but thinking's moved on. I mean, we used to think of Mars as the obvious place in the solar system where we would want to look for life, but I hope to try and convince the few doubters there seem to be in the room that icy moons are better places. And before I get to my slides, I'll tell you why icy moons are better places to look for life. There's plenty of them. They've got a high potential today to host complex, vibrant ecosystems. Don't really think that of Mars. There's good evidence of the long-term prevalence of conditions inside these icy moons, conditions such as where we think life on Earth probably began. We've got hot vents on the floors of the oceans inside these icy moons, almost certainly, and that's the best bet for where life on Earth began. So it's likely we're able to start life there if we can start life on Earth. And we don't even need to land on these icy moons, because at least 2 of them are jetting stuff out to space. We can just fly through it and sample it. And the other point about icy moons is the significance of finding life. Why do we want to look for life? I agree with Suzanne. Are we alone? We want to know if this is the only place in the cosmos where there is life. We now know that 1 star in every 5 pretty much has a planet which is likely to be habitable. We don't know if life has got started on any of those places. The best way to find out how likely it is that life will start in a habitable environment is to find another habitable environment where life has started, independent of the Earth. If we find life on Mars, it's going to be a lot of work to assure ourselves that that isn't life that got there from Earth on a meteorite, or the other way around, did life arrive on Earth on a meteorite from Mars. Earth and Mars have been swapping bodily fluids for the past 4.5 billion years. They're contaminating each other. The icy moons are much further away and much more gravitationally sealed off from the inner solar system. If we find life on an icy moon, its significance from the get-go will be a lot greater than if we just find life on Mars, because it'll be almost certainly an independent genesis of life. If we find life started two places independently in the same solar system, then all those habitable planets we can see out there are likely to be inhabited as well, is what we'll be saying. So let's go on to the slides, please. So Mars, you've seen what Mars looks like. It's got an arid surface. If you want to find life, you've got to go inside the planet rather than at the surface. That's true of the icy moons as well. Let me show you the icy moons which are most likely to be hosting habitable environments. Next slide. So the four best candidates: Ganymede, the biggest moon of Jupiter, where models suggest several layers of ocean under the icy surface with different phases of ice in between. Titan, the biggest moon of Saturn, it's got lakes of methane. That's not where we're thinking of life. There's an internal ocean inside Titan. Europa, a largish moon of Jupiter, a rocky body, lots of tidal heat, and at the top we've got ice and an ocean below, and almost certainly hot vents on the ocean floor. And then Enceladus, tiny moon of Saturn, but hey, it's got really dynamic plumes jetting out the ice crystals to space, and we think there's a global ocean in there as well. So those are the best candidates. Next slide, please. So here's Enceladus, global ocean we now think under the ice, South Polar region, plumes jetting out to space. If there's anything living in these oceans, fly through that plume, you'll find dead microbes in the plume material. Next. So here's the evidence for oceans. The surface is decoupled from the interior. That's been proved in the case of Titan and Enceladus. There's a magnetic field generated in the ocean, Ganymede and Europa and Enceladus. There's auroral features which are interpreted as showing where the ocean is in Ganymede. There's gravity modelling. There's surface cracks showing the surface is mobile. There's plumes erupting to space from Europa and Enceladus. And in the plumes of Enceladus, we've got evidence of water-rock interactions. That's important. If the water inside is reacting with the rock, we've got chemical energy which can feed the microbes, which are the base of the food chain, which we then hope to find jetted out to space. Next. And so here's a real image of plumes on Europa. Many plumes at once. Fly through those, find dead microbes. Next, we also have plumes on Europa. This was big news just a few months ago. The plumes on Europa are much more elusive. They're ephemeral, but they do exist. We know that now, so we can sample those plumes as well. Next. And so inside Europa, we see, we envisage an ocean below the ice with rock above, and where the warm rock has the ocean sitting above it. This is what we would hope to find there. Next slide, please, which should be the video. Let's play this video. This is a hydrothermal vent. Play the video, please. Hydrothermal vent on the Earth's ocean floor. There's a chemically rich waters there, precipitates forming. This white stuff here is microbial life. You might see a few shrimps and crabs and tube worms around. Higher organisms, these crabs are grazing on the bacteria. This is an ecosystem. If you switched off the sun, life on Earth wouldn't die out. It will continue around these hydrothermal vents. And this is where we think life on Earth began, and we think we've got places like this below the ice, inside the icy moons. So this is the basis of an ecosystem. Next slide. Surface of a place like Europa. The ice opens and cracks tidally, and these double ridges are where slush is squeezed out when the cracks close. So you've got potentially tombs for the dead microbes in these slushy ridges. Next. So we can imagine in these cracks photosynthetic life. When the cracks are open, there's enough sunlight there to feed plants and grazing animals. And when the cracks close, they're squeezed out to here. But also, of course, we've got the photosynthetic and the chemosynthetic stuff erupted to the surface through these plumes. Next slide, which I think is my final one. Just fly through it here, and we'll finish with the last slide of all, which sums up why icy moons are good. Abundant liquid water inside. More water in Europa, liquid water than there is on the Earth's oceans. Chemosynthetic life is eminently viable. There's multiple present-day habitats there, and there's no need to land. Just fly through the plume and sample it for free. Thank you very much.
Thank you. Right, well, the ball is now back in the Mars court, so if I could ask Monica to step up and make her case for Mars. Thank you, Monica.
Dead microbes entombed in a plume. I mean, I ask you, it's not exactly making a great case for a habitat, is it? And, you know, photosynthetic organisms in cracks. It's like, yeah, photosynthesis, yeah, from the sun, radiation. Those moons that Dave was talking about, they're around those giant planets, the most inordinate amount of radiation. Really, really dangerous. No wonder all the microbes are dead when they come out of the plumes. There's very little chance of anything surviving on the surface of those bodies at all. But let's go back to Mars. You know, let's not diss the opposition, because the idea is to convince you with positive arguments. Now, my first slide, when it arrives, is going to show another part of the surface of Mars. And this is from the Viking, it's Viking 2, lander from 1977. And for those of you in the audience who might remember back to 1977, and looking at you, I can see there's very few of you who would actually remember that. But Viking landed, made some scrapes on the surface of Mars, did some experiments, did the first experiments on the surface of Mars, and found signs of life. Maybe. Unfortunately, over the intervening years, the debate about whether those results were correct or whether they were an analytical artifact or the chemistry wasn't understood has gone on and on and on. And the balance is that actually they didn't find life. But what they found was sufficiently encouraging to propel the arguments forward. And we've been carried with those arguments. This is why Colin Pillinger works so hard with Beagle 2. Next slide, please. In the intervening time, there have been several different missions going to Mars. And this is another picture from Curiosity, from the Gale crater. Because what we found is the byproducts of life in Mars's atmosphere. And this is something which is really, really difficult to explain by any other way than life. And that's the discovery of the gas methane. Now, methane, CH4, is produced inorganically, you know, so not by biology, by the action of water on rocks, okay? So if you've got running water and you've got rocks and you weather the rocks, you produce methane. You've got to have the running water. Now, Suzanne showed very beautifully that there is currently no huge swathes of running water. So methane should not be being produced on Mars at the moment by that method. The other way of producing methane is biologically, and that's by a byproduct of digestion in cows and termites. It's produced in paddy fields by rice and so on. Methane has been found in Mars's atmosphere. Now, methane in Mars's atmosphere, it would react away instantly because of the rest of the chemistry of Mars's atmosphere. But it's there. Curiosity has detected it. It's been detected by telescopes on Earth. There is methane on Mars, and it's being continually produced. Next slide, please. The Trace Gas Orbiter was launched last year and in October, and later on this year it will arrive at its final orbit around Mars and start measuring the distribution in Mars's atmosphere. We'll start to look and see if there are seasonal differences in the production of that methane. Next slide, please. Now, if there are organisms on Mars, it's going to be very difficult for them to live on the surface. Susanna showed that because of the sun's radiation. But they can live below the surface. One of the continents that has the largest biomass is Antarctica. We tend to think of Antarctica as being frozen, covered in ice, but a large part of Antarctica is dry. The dry valleys, they are sandstone, a lot of them, and they have, in the surface of those rocks, a huge amount of biological matter. Here's a picture. you can see, it's a bit bright here, so it's not so easy to see, but you can see a light layer here and more orangey on either side. This is a sandstone from part of Antarctica, and inside it, 2 minutes, inside it is a symbiotic relationship, an organism, a lichen, which is there, it's a cryptoendolith, crypto, hidden, endo, inside, lith, a rock. It's a system of bacteria and fungi working together. One of them uses photosynthesis to produce energy. The other produces a compound which prevents it getting too sunburnt. So you've got a system here living in the first centimetre or the first half a centimetre of rocks in Antarctica. Next slide. Antarctica is this barren place, but it holds this huge biomass. Now Mars, this is a picture of a hole on Mars, okay, about 200 metres across. It's a cave. There's a whole series of caves in the sides of some of the volcanoes. Now, on places like Hawaii, there are volcanoes and there are great big caves which go down, and there are life in those caves. So life could be present still on, below the surface of Mars. Final slide. It's my penultimate slide. We have, to all intents and purposes, seen fossilized bacteria in carbonates from Mars. This is a Martian rock. It's possible that there are many, many different types of bacteria living on Mars. Final slide. 2 of these pictures are the surface of Mars. 2 of those pictures are the dry valleys of Antarctica. I'll leave them with you. Which is which? Could you tell which of those is the habitat of a huge biomass and which is a so-called sterile planet? You can't tell the difference. Mars isn't sterile. It's just waiting for us to find the life there. Thank you.
Thank you, Monica, for making a compelling argument for Mars. Now, I can see that Dave and Karen have been plotting during your presentation, so I'm going to hand over now to Karen to continue the case for icy moons. Thanks, Karen.
And before I start, I would just like to point out that I'm the microbiologist here. So I study microbes in extreme environments. So this is what I'm going to talk to you about, is it from my point of view and why I think icy moons are a better place to look for than Mars. And I will actually have to shoot some of Monica's arguments out of the water as well, just to. First slide, please, Jessica. And I apologise for my voice. So there's 3 points why I think the icy moon's a better place to look. There could potentially be an independent origin of life. They could support complex ecosystems, and finding evidence of life is a lot easier. Now, I'm going to take the next 5 minutes to convince you of my arguments. So, independent origins of life. So the question we're here to ask is which is better to look for? So to me, actually finding somewhere which has an independent origin of life, an independent genesis, is a better question. If this happens, those planets that Dave mentioned, that potential habitable environments, could actually be habitable. And that is the holy grail. That's what we're here to understand. Is there life elsewhere in the universe? Or have we accidentally contaminated Mars with life from on Earth? That's what we need to answer, really. Now, for life to exist, it would either have to evolve independently with an independent genesis or been transferred from Earth. Next slide, please. So, there's been a lot of work, video please, about studying how life evolved on Earth. What we know, what a recent hypothesis suggests, that in these deep subsurface oceans, we have these hydrothermal vents. And they have complex chemicals which are the precursors, the conditions to produce the precursors for life, the prebiotic molecules which we need for life to evolve. And we think that they're there on the icy moons and the deep subsurface. Potentially, they could have been there on early Mars, but they probably wouldn't have been long enough for life to evolve. So when we think of Mars, which is more likely than the icy moons, because the icy moons oceans are protected by the ice, we think that life could be contaminated from Earth. This is where life could have hitched a lift on a rock and seeded these early Mars environments that Susanna mentioned. But that's not really of interest, is it? Because that's showing that we've just contaminated the solar system. What we want is an independent genesis. Next slide, please. So we know what Dave mentioned, that we have these hydrothermal systems can exist. Next slide, please. So what do we need? Okay, so we know that there could be potential life evolved on Mars and the icy moons, but what we know that we need, based on what we know about Earth, it needs liquid water, copious amounts of liquid water, it needs essential bioessential elements, and it needs an energy source. Next slide, please. Next slide, please, sorry. First video, please. So imagine that we have what we're looking like on the icy moons. So here we have these hydrothermal vent systems, which can produce these chemicals which can be used by microbes to produce energy. And it's not just energy from these microbes, they're not just they can produce enough energy for these complex systems. Whereas on Mars, if we have present-day life, it would be limited to the subsurface environment where there's only going to be limited amounts of energy sources. So you're not going to get these complex systems. Also, as Susanna mentioned, and what Monica mentioned, they're going to be in these cold environments. There's going to be a small amount of transient water could exist. But there won't be much microbes there. And Monica mentioned that there's lots of microbes in Antarctica. But when we compare them to the oceans on Earth, it's tiny. For example, if you took 1 ml of seawater and counted the amount of different microbes in there, you'd get about 140 different species. But it's not just that. If we're playing the number game, you take 1 ml of seawater, and there's approximately 1 trillion microbes per ml of water. So if the oceans of these icy moons are even a little bit similar to what we have on the oceans on Earth, we're going to get a large number of microbes present, a lot more than what we would find on Mars. So actually finding evidence of life would be a lot easier. Which brings me to my final point, that if we want to find evidence of life, not just evidence which is a bit wishy-washy, is there methane, is it not, is it abiotic, is it not, Alan Hill Jr., potential microfossils, actual real evidence, which is what we're after really, isn't it, at the end of the day, we should go to the icy moons. Because these plumes that we talk about, microbes can be expelled from these plumes, giving us a snapshot of what's happening in the oceans, but they're going to be protected from the detrimental conditions of the environment. Whereas in contrast, when we look at Mars, anything on the surface is going to be broken down, destroyed. This is why we just talk about the Viking lander. We don't know about these organic molecules if they're in fact
Keep going.
alive or not. So these are the questions that we need to ask. So if we want to find definitive answers, we need to go to the icy moons. Because it's not just, when you think about it as well, Susanna mentioned that we could have these transient water environments in the subsurface. But let's just think about this logically. You have a lander. Remember, a couple of months ago, we're not that good at landing on Mars, just a point. We have to land. We don't just have to land. We have to drill a hole through the regolith and find a transient environment where there's little amounts of potential water in these potential clay molecules. You're looking at tiny amounts of water. But you look at the oceans. You take Europa, for example, there's 4 times as much water on Europa than there is in the oceans on Earth. So if you do the maths and you think about this logically, the icy moons is the better place to look. Next slide. I think the slides aren't in order, so this is the final slide. So going back to my first slide here, these are the points why I think we need to look at icy moons. An independent origin of life, which is actually a better scientific question, isn't it? Because it's opening up a whole world for us. It can support complex ecosystems. So we're not just looking at one microbe here or there, we're looking at complex ecosystems. This is really exciting for us. This is what we need to be looking for. And also finding evidence, definitive evidence, not just something we're going to spend the next 20 years discussing, is it or isn't it? We need to go to the icy moons. And my voice is held out, and that's my argument.
Yes, thank you, Karen. It's testimony to your passion that you managed to keep going all the way through that. Well, you've all heard the 4 arguments for and against. So what we'd like to do next is open up the session to everyone here in the audience and all of you online and take some questions. So we'll start in the room. If gentleman down here.
Do I need a mic?
Yeah.
Hello, panel. My question is, if microbes were found on either Mars or an icy moon, would you consider quarantining it? And if not, how complex would life need to be before you would consider quarantining it from Earth probes and possibly astronauts going to those places?
Can I answer that one?
You can try.
So this is one of the problems when we think about Mars, is about the sample return missions to Mars, is the fact that to actually, I mean, you might be able to answer more about this, but we'd actually have to get rid of the microbes before we're allowed to look at them, aren't we, on Earth?
Well, but at least when we're talking about Mars, we have the likelihood of going to Mars and bringing a rock back to test. The chance of actually going to one of the icy moons and making those tests and bringing something back is absolutely zero in the next century. So the idea of quarantining something, should it exist, from an icy moon is not something that we even bother to consider, because it's just so unlikely to be happening.
But there are clear rules. There is the planetary protection, which set out clear rules for what you have to do with whatever you bring back. And so you might remember that the Apollo astronauts went to quarantine because no one knew what to expect. And there would be similar procedures no matter from which place we would bring something.
At the moment, we're not allowed to land on an icy moon because of the forward contamination from Earth to the icy moon. This is why the Galileo probe to Jupiter was crashed into Jupiter rather than leaving it as a derelict in orbit, which might eventually bump into a moon. Which is why having a place with eruption plumes is great, because you don't have to land. You can sample the potential life without touching the surface, so you're avoiding the COSPAR planetary protection protocols, which prohibit you from landing in potentially habitable environments. But both Mars and icy moons, you've got problems with bringing material back under current rules. Yeah.
Thank you.
Okay, so we've asked for your questions online as well, so I'm just going to turn to the guys here. Have you got any questions for us from the online audience?
Yeah, and thanks everyone for getting involved. We've got people from all over Europe, North America, and even some people getting involved from Australia. So first question comes from John in Melbourne. He says, we hear a lot about the icy moons of Jupiter and Saturn, but are there any candidates for potential life around, say, Uranus or Neptune?
Dave, are you going to take that one?
I'll take that. Yes, but they're less likely. There are plumes on Triton, the big moon of Neptune, but they're not from an internal ocean. We think they're just from underneath a nitrogen cap. So really, the best candidates are the four I showed on here: 2 of Jupiter and 2 moons of Saturn.
Well, Melbourne isn't quite as far away as the icy moon, so we'll take another question from in the room, please. Yes, lady here. Can we get the microphone in, please?
Thank you. I just wondered, the thermal vents on Earth are because of tectonics, so how do you know that sort of stuff's going on the icy moons to create the conditions for thermal vents?
You're right, most of the hydrothermal vents that we study are because of plate tectonics, seafloor spreading, but any volcanic process with hot rock below the ocean floor will draw water down and jet it out. And we think of Europa as a slightly less active version of Io, the innermost moon of Jupiter. The 4 inner large moons of Jupiter are all in orbital resonance with each other, and there's tidal heating going on. So you've got tidally heated rock, you've got hot rock, you've got enough heat there to draw water down and chemically interact with the rock. So this is why the oceans are there, not frozen. You've got heat coming in from below. So that's the logic. You don't need plate tectonics, you just need hot rock.
Thank you. Peter, have you got a question?
Yes. So this is from Sebastian Sjorstrom. I'm sorry, I don't know how to pronounce your surname. But the origin of life is probably unlikely, given that we don't observe any with telescopes. Isn't it more likely that we will find terrestrial contaminants rather than actual alien life?
Monica, do you want to take a lead on that?
Right, well, that's interesting. We haven't found signs of life with telescopes. Well, it's only been in the last, decade that we've started to really nail down the type of planets that are round other stars. And it's only in the last couple of years that we've been able to see Earth or a little bit bigger than Earth-sized objects up until a few years ago, all we could see were things the size of Jupiter, which were as close to the Earth, close to their stars as Mercury is to ours. So it's not really been surprising that we haven't actually observed life on planets beyond our own solar system, because we haven't been able to observe the right sort of planets up until very, very recently. And also you've got to start thinking, well, what are you going to be looking for if you're going to be looking for life on planets beyond the solar system? I mean, there's a search for extraterrestrial intelligence, but I don't think we're going down that route in this debate, because that's sort of got different criteria. But looking for the biomarkers, the biosignatures, that's very, very difficult when we can only just start to detect the atmospheres, let alone changes in the atmospheres of these planets, which is the sort of place where you're going to be looking for things like methane and disequilibrium assemblages. So it's not really surprising that we haven't found it beyond the solar system yet. I think, you know, give us time. The technology is getting better and better all the time as we, you know, look at the next generation telescope, which will be launched 2018, the James Webb. That should be, you know, that will help in producing some more of the sort of data that we need to know.
Monica, thank you. We'll take another question from in the room if anybody... Yes, lady here, please. Just wait, microphone's heading your way.
Thank you. There are found on dust grains between the stars amino acids. Can you give us some idea of how they're formed and whether it can go on to developing lifelike characteristics?
Okay, shall I take that one?
Yes, you can jump in.
Okay. I mean, in the space between the stars, in interstellar space, there is a huge chemistry that goes on. I mean, most of the gas that's out there, you know, it's very, 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 very low density of gas and particles. It's mainly space, but where there are particles, it's mainly hydrogen. But you have radiation from the stars, and you have all the other elements out there as well. And so you get this chemistry that goes on at very, very low temperatures, and you have the icy grains acting as a substrate and a catalyst. And you have ice, water ice, carbon dioxide ice condensing on the grains. You have ultraviolet radiation. You have a whole massive chemistry going on. Yes, you have amines, you have carboxylic acids, you have great long chain molecules. So far, there has been no suggestion that there's a complex molecule like DNA, because the processes which depend on ultraviolet radiation can break bonds as well as make bonds. So you get to a sort of equilibrium stage, I think, where you can't get to build all the different bits that you need to make something living out there. You've got all the different molecules, but you've got no way of collecting them together and having them react with each other like they do in a cell on the Earth. So yes, the building blocks are there for absolute definite, but not anything that we would recognise as being alive.
Okay, thank you. We'll take another online question if you've got one.
We have a question here from Hugh Harkins. He says, I understand there are promising areas of Mars that we're not allowed to explore for fear of contamination. Is there a way that this could change in the future, or how would you shape that?
Suzanne?
Yeah, not allowed to explore depends on the spacecraft you bring. Because you bring a spacecraft that's made for the purpose. For example, the Curiosity rover that's driving through Gale Crater wouldn't be allowed where the Phoenix lander was, simply because the Curiosity rover has an RTG, a radioactive power source, which keeps its own warmth for many, many decades. So you wouldn't go to the polar caps with that rover because of the warmth it brings with it. However, if you land with a Phoenix lander with solar panels, you are allowed to land there because that will freeze over as soon as there is not enough sunlight anymore. And so you build your spacecraft for the purpose you want to explore, and you can also sterilize a spacecraft for the purpose you want to explore. That's why the Coast Guard regulations are there that we have mentioned earlier. And so there are international treaties that regulate what you can and can't do and what is considered safe to not forward contaminate Mars.
Too, but there's been a lot of work that looks at microbial growth in these clean rooms, and it's very, very difficult. We don't, well, even the instruments we've sent already, there is contamination on them. So although it's not on purpose and we have tried to sterilise them, we are sending microbes on the instruments.
Thank you. I'll take another online question.
Okay, so this is from Ian Watson in Norfolk, and he wants to know which of the icy moons would be most likely to support life.
Dave, do you want to take that one?
Most likely to support life, I would say Europa, because it's large, big ocean, more tidal heating in Europa. Easiest to sample Enceladus because it's got persistent plumes, but most likely to support life, Europa. I'd like to get a submarine through the ice to go sniffing at. No, it'll happen one day. You can find hydrothermal plumes in the Earth's oceans with an instrument called a nephelometer, which looks at how turbid the water is, and you home in on the suspended particles. You could find these vents with the right kind of robot submersible in Europa's oceans. The simple answer, most likely to host life, Europa, but not the only one.
I like the idea of ambitiously getting a submarine out there. I'll take another question from in the room, please, if anyone's got one. Yes, gentleman here. Just wait for the microphone to come in.
We know there was a large percentage of water that covered Mars all those billions of years ago. Is there any chance of any significant bodies of water surviving maybe on the subsurface of Mars, or is it just simply too hot?
It depends on how deep you go. First of all, we have a thinking of Mars. It's frozen at the surface or dry. You have then a cryosphere layer, depending on where you are, because Mars is a planet just like the Earth. So you have the colder areas at the poles and the warmer areas at the equator. But you also have a planet, and all planets get warmer the more you get to the inside. And so what you need to think about, you've got this outside, which is maybe cold and dry or cold and wet at the poles. But then the deeper you get, the warmer it gets, at about 13 degrees C per kilometer. So if you think of minus 60 degrees C on the surface, you don't have to go all that deep to actually make that water liquid in the pores. And we know from Earth that at the deep drilling projects, we have liquid water at many, many kilometers down in the rocks on Earth. So we kind of expect liquid water down there.
Okay, thank you. We've got a couple of minutes left, so we'll take another online question, please.
So we have one here from Mark. He says, I have a question for the Mars team. If the subsurface is the right place to look for life, why have we not already found it?
We haven't drilled deep enough. I mean, there have been only, I think, is it only Curiosity that has taken a decent-sized drill there. Pathfinder didn't scrape the surface. Phoenix scraped the surface, but nothing has drilled really deep down. We saw the drill hole that Susanna showed the picture of, and that's only a few centimetres deep. The ExoMars, which should launch in 2021, I think.
2020.
2020, is going to take a drill that's at least going to go down at least 2 metres. So you need to go down deep to make sure that you're getting through the regolith into the rock, to make sure that you're getting away from anything that has been altered by radiation. We don't know what that level is, but we reckon 2 metres should be a good bet.
Okay, anyone else want to comment on that? Dave, I saw you making a note.
That's for later.
Okay. Keeping your powder dry for the moment. Okay. Well, that's pretty much taken us to the end of our question and answer session. So thanks to the audience here in the room for your questions, and thanks to all the folks online, and the academics will be available to continue and answer questions once this live session is finished. So what I'd like to do now, and you've got 2 minutes each, so I'll be clock watching again, is ask Dave to sum up the argument for icy moons and Monica to sum up the argument for life on Mars. You can go in whichever order you choose.
I'll be a lady and allow the gentleman to go first.
Dave, over to you.
Well, Mars started, so I thought Mars was coming now, but fair enough, 2 minutes. Monica, I thought you were a better scientist than this. You say it's too dark at Jupiter for photosynthesis. Jupiter is 5 times further from the sun than the Earth. So the sunlight is 5 squared, 25 times less. It's like a cloudy day on the Earth. There's enough sunlight there for photosynthesis. 2 meters below the ice or below the water in the temporarily exposed crack, you're free of Jupiter's radiation. You're right, the surface is very hostile radiation-wise. 2 centimetres of water, you've got plenty of light and you're radiation free. You could have photosynthetic life in these cracks. But I'm not pinning my hopes on photosynthetic life. This is a transient environment, still more permanent than any environment we envisage on Mars at the surface today. But still, the big thing about the icy moons is the abundance. I mean, Karen made the point so well in her marvellous squeaky voice. You get in vast volumes of water, potentially vast numbers of microbes per cubic milliliter. But we get down to where we know there's water resting on warm rock, hydrothermal circulation, chemical richness. That's the place to go. It's far more likely to be life there. And that's going to be life, which if it does exist, is almost certainly life that's arisen from a genesis that's independent of life from Earth. Okay, it may have been seeded by amino acids delivered by meteorites, and that's the same throughout the solar system, the same throughout the cosmos, we imagine. But starting life going is what we don't know about, which is why finding life in an icy moon is going to be vastly more significant than finding life on Mars. It might be more expensive, it will take longer, but it's going to take a longer drill than 2 meters to get to liquid water on Mars, that's for sure. Liquid water on an icy moon is jetted out to space where you can sample it. So the environments are there for sampling. Let's go and see if there is life or is not life elsewhere by sampling plumes from icy moons. Thank you.
Dave.
Really, Dave, I thought you were a better scientist than this. To talk about cubic millilitres. Yes, you did. Yes, I grant you, icy moons are a really great place to look for life, but it's going to take a long, long time to get there. Very, very expensive to do. I mean, there's a mission which is going to Jupiter, which is going to launch fairly soon. It's not going to be arriving there until about 2034. You know, these are the sort of time scales that you've got to think about when you want to actually make these measurements. Mars is relatively close. It only takes 9 months to get there. It's a sort of place where you can go, you can make your measurements, you can make discoveries, plan the next mission, plan the next mission, plan the next mission, all before you've actually managed to get even close to Jupiter to make any sort of, flights through these ephemeral plumes, which may or may not be lasting for a significant length of time. Yes, it will not be easy to find life on Mars. But when you think about how Mars has evolved in the same way that the Earth has evolved, from the same starting materials that Earth has evolved from, in the same part of the solar system that the Earth came from, Mars has had all the ingredients. It's had the geological processes, it's had the water. It surely must have life. And I really, really, really believe that we will find signs of life on Mars very, very shortly. Thank you.
Thank you, Monica. Right, well, that's the end of the debate, and it looks like the conclusion is we either need a very long drill or a submarine. I'd like to thank all of our speakers, and of course all of you here in the audience for taking part, and all of you online for taking part as well. I think what we'll do now is a final poll to see if our speakers have compelled anyone to change their minds. So, those of you online, use your voting widgets again and vote now. And those of you in the audience know the drill. Wave your icy moon or your Mars card at me. Guys, what do you think? I'm thinking icy moons.
I'm thinking there's a lot more Mars than
But
there
you
was.
are right, Monica. There are a lot more Marses, but I think icy moons are still claiming the day in the audience. So we'll post something online afterwards and let you know the results of the final poll. So do keep voting online. Okay, folks, well, it comes to me to end this session, but also to say, those of you in the room and those of you online, if you want more of this kind of activity and live interaction, please let us know through all the online channels available to you. And for those of you who are studying S111 with us, do not forget the cut-off date for your TMA2 is next Wednesday, folks. Ladies and gentlemen, it remains to me to say a special thank you to all of our speakers. Give them a nice round of applause. Thank you. The S111 module team, thank you. And all of the production team in the studio today. Thank you very much. And that's the end of the session.